Let's continue. Question 19. What is the pressure inside the drop of mercury of radius 3 millimeter at room temperature? Surface tension is given. Atmospheric pressure is given. Also give the excess pressure inside the drop. So first of all, we can calculate excess pressure inside the drop. We can have Pi minus P naught is equal to 2S by R. You can substitute the values of S and R, and you can find the value of excess pressure. Here the pressure outside is the atmospheric pressure. Therefore now the pressure inside you can calculate using the same formula. Pressure inside is equal to pressure outside, that means atmospheric pressure plus 2S by R. So you will get the answer. Now, question 20. What is the excess pressure inside a bubble of soap solution of radius 5 millimeter? Okay, given that the surface tension 2.5 into 10 power minus 2 Newton per meter. Now, here also you have to calculate the excess pressure. So use the same formula. We have Pi minus P naught is equal to, here it is an air bubble. Sorry, it is a bubble of soap solution. So it's a liquid bubble, not the drop. Therefore, we have to take 4S by R, because a liquid bubble has two surfaces. You have to take 4S by R, and the excess pressure can be calculated. Then again, for an air bubble of the same dimension were formed at a depth of 40 centimeter inside a container containing the soap solution of relative density 1.2. What would be the pressure inside the bubble? Okay, so here in the case of air bubble, our formula is Pi minus P naught is equal to 2S by R, because air bubble has only one surface, so you will get 2S by R. Now what is the pressure outside? P naught. So the pressure outside will be, first of all, we know atmospheric pressure will be there. Okay, and along with the atmospheric pressure, it is formed 40 centimeter inside the container of soap solution. So a 40 centimeter height solution will give a pressure H rho G, where rho is the density of the soap solution. It is given 1.2 is the relative density. So the density is 1.2 into 10 power 3 kilogram per meter cube will be its actual density. So you will get the value of P naught. So, and what you have to calculate, what would be the pressure inside? Pi you have to calculate. So you will get Pi is equal to P atmosphere, the value of atmospheric pressure you have to substitute, plus H rho G, pressure exerted by the soap solution, plus 2S by R. 2S by R. So you can calculate the pressure inside. Then next, a tank with a square base area 1 meter square is divided by a vertical partition in the middle. The bottom of the partition has a small hinged door of area 20 centimeters square. The tank is filled with water in one compartment and an acid of relative density 1.7 in the other, both to a height of 4 meters. Compute the force necessary to keep the door closed. Okay, so let me draw a two-dimensional picture here. So we have the water tank, square-based tank. However, this is only a two-dimensional diagram. Okay, and the tank has a partition in the middle. So here there is a partition at the middle, and the partition has a door at the bottom, and the door has an area of area is given, it is 20 centimeters square area. The door can be opened like this, in this way. So like this, the door at present it is closed. Okay, and now what's the difference? Here you can see one of the compartments is filled with the water and the other compartment with the acid. So water compartment, and we can have the acid compartment. Both are having same height. It is given 4 meter. Okay. Now here the pressure applied by water, we can calculate pressure applied by water is equal to HW rho W G, while the pressure applied by acid is equal to H, the height of acid, rho of acid into G, but both the heights are equal into G. Now you can see water having relative density 1, while that of acid is 1.7. So height is same, G same. So acid has high relative density, definitely. Pressure applied by the acid will be high. As pressure applied by the acid is high, then what happens? So a high pressure is there in the acid side, while you can have a low pressure in the water side. Naturally, what happens to this door? This door will open towards the water compartment. The door will open towards the water compartment because of the pressure difference. High pressure in acid compartment and low pressure in water compartment. And if you want to keep the door closed, then what you have to do? You need to apply a force here to keep the door closed. A force must be applied. Then how much is that force need to be applied so that you can keep the compartment closed? That is the question. So here what you have to do? You have to calculate the pressure difference. So you can calculate the pressure applied by water is equal to HW rho W G. Then find the pressure applied by acid, H acid rho acid G. Then find the pressure difference. Okay, and the force is equal to, which you need to calculate the pressure difference, PA minus PW. PA minus PW into area of cross section A. So you can find the force required to keep the door closed. Question 22. Diagrams are given. Okay. The part both are manometers, and the diagram A give the absolute and gauge pressure of the gas in the enclosure for cases A and B in units of centimeter of mercury. Remember atmospheric pressure PA is equal to H rho G, where H is the height of the mercury in the manometer, that is 76, and rest you can substitute the density of atmosphere and density of mercury and G. So you calculate the value of atmospheric pressure, and rho is the density of mercury, and G is isolation due to gravity. Assuming these two quantities are constants, we can express atmospheric pressure in terms of centimeter of mercury. So accordingly, atmospheric pressure is, we can say, only H we can consider, taking other quantities constant. So atmospheric pressure is 76 centimeter of mercury. So pressure you can express in terms of centimeter of mercury. Okay. Now here, first take the diagram A. When you take diagram A, you can see here there is a horizontal height. And we can take pressure. P is the pressure inside the container. So everywhere pressure is P inside. And here we have atmospheric pressure. PA is there. Atmospheric pressure PA. So pressure at this point can give the name point A and point B. Pressure at A is equal to pressure at B is equal to pressure P. So that is our concept. Pressure P is equal to pressure at B is equal to pressure at A, and pressure at A is equal to the pressure applied by 20 centimeter of mercury. So as we have seen here in the case of atmospheric pressure, that I will write only as 20 in terms of centimeter of mercury, 20 centimeter of mercury plus atmospheric pressure, that is 76 centimeter of mercury. So therefore, here you will get the pressure inside the bulb is 96 centimeter of mercury. 96 centimeter of mercury. Now that is the total pressure. Now gauge pressure you have asked to calculate. How do you get the gauge pressure? Gauge pressure is equal to total pressure minus atmospheric pressure, which means it is 96 minus 76, so that 20 centimeter of mercury will be the gauge pressure, 20 centimeter of mercury. Now apply the same concept for diagram B also. We have the horizontal line here. Now here we have the atmospheric pressure 18 centimeter of mercury and take pressure P inside the container. Now here you can see atmospheric pressure is equal to, we have to make the equation. So pressure at A is equal to pressure at B. So PA is equal to PB is equal to P pressure inside the container or the bulb, water pump, whatever be, plus pressure of 18 centimeters of mercury, which is 18. Now PA, you know, atmospheric pressure is 76 centimeters of mercury is equal to P plus 80. P you have to calculate. So P is equal to, you will get 76 minus 80. So you will get the answer 54. So you will get the answer 58 centimeter of mercury. Okay, now that is the total pressure. Now gauge pressure you have to calculate. Gauge pressure is equal to total pressure 56 minus atmospheric pressure. So you will get the answer minus 18 centimeter of mercury is the gauge pressure. Now part B, how the level change in case B if 13.6 centimeter of water immiscible with mercury are poured into the right limb of the manometer. 13.6 centimeter of water. Okay. So we can calculate the equivalent height of mercury. How can you calculate the equivalent height of mercury? What is the equivalent height of mercury for 13.6 centimeter of water? Can take like this: HW rho WG is equal to HM rho mg. Now, what will be the corresponding height of mercury for 13.6 centimeter of water? Water relative density is 1. Okay, here itself G will be cancelled. So this is equal to Hm, which we want to calculate. Relative density of mercury is 13.6. So what is the answer you will get? You get the answer Hm is equal to 1 centimeter. That means 13.6 centimeter of water is equal to 1 centimeter of mercury in terms of pressure applied. So we can see if you add 13.6 centimeter of water, it will impact 1 centimeter change on mercury. So what happens? Already you have 18 centimeter level difference is there in the mercury in manometer. Now when you add water here, that water is able to make a difference in mercury level which is equal to 1 centimeter. That the weight of 13.6 centimeter of water can make 1 centimeter of level change in mercury. So then what happens to the difference in mercury level? You have 18 plus 1. The difference in mercury level will be 19 centimeter. Okay. Now, question 23. Two vessels have same base area but different shapes. The first vessel takes twice the volume of water that the second vessel requires to fill up to a particular common height. That means the liquid in both the containers are at equal heights. Is the force exerted by the water on the base of the vessel the same in the two cases? If so, why do vessels filled with water to the same height give different readings on the weighing scale? Okay, so here we can take two containers. The first container and the next one, second container with the same base area. Base area is same, but you see its volume is almost double. So you have to take the container like this. Then both of them were filled with the same height of liquid water. Same height of water. Both are having same base area. You can take as A. Here also base area is same A. Then both of them having same height of liquid inside. Height H. Now if height is H, then pressure is equal to H rho G. Pressure is equal to H rho G. So both are having same pressure at the bottom, H rho G. So in both the containers having water with the same height. Then force is equal to pressure into area. Both are having same area of cross section at the bottom. Therefore, what about the force exerted by the water on the base area? So both are having same force. So in the first vessel and the second vessel, the force acting on the base area will be same, P into A, because both are having same area, base area, and both are having same pressure. So it will be same in two cases. Okay. But at the same time, question says that, and definitely, in the second container is having water almost double. Okay. The volume of water is double in the second container. Now, so force is same. Both are having force F on the base area. Now, the next step, both these containers placed on weighing machine. Placed on weighing machines. Now, the same force is acting at the base area. Now, the question is whether the weighing machines will show the same reading or not. Because weighing machine is measuring the force acting there. We have got same force is acting. But if the first one is having 10 kilogram of water, second is having 20 kilogram of water, then will you get same measurement in the weighing machine? As force is same on the base area in both cases. Answer is no. Reading of the weighing machine will be different. Even though the force or the base area applied by water is same. Then, reason. What is the reason? Because when we calculate this force F for the sake of finding pressure, then you see here everywhere the force is acting normal to the walls of the container. Here also, like this. Now this force we can resolve into perpendicular components. Okay, force can be resolved into perpendicular components. We have horizontal component and vertical component. Here also horizontal component and vertical component. And when you calculate pressure, actually what happens is horizontal components are cancelled. And this force you have obtained only from the contribution of vertical components, in such a way that the horizontal component acting on the walls of the container is cancelled when we think about what happens inside the container. But when we think about what happens outside the container applied by gravitational force there, then we have to consider the total force. There is no cancellation. You are measuring the whole vessel. You need not take any cancellation. Whatever force applied there, okay, we need to consider. It is not, when you calculate gravitational force, it is not like the force that you have calculated for calculating the pressure on the base area. The whole forces, no cancellation there. The entire force applied by the liquid will be measured. Therefore, this type of cancellations are not applicable when we measure an external force acting on the liquid and the container. The whole force will be measured. The whole force when you measure, here you have a 20 kilogram of water, so measurement will be 20 kilogram each. Here 10 kilogram of water, so measurement will be 10 kilogram each. Therefore, the measurement on the weighing scale will be different in these two cases. Next question 24. During blood transfusion, the needle is inserted in a vein where the gauge pressure is 2000 Pascal. At what height must the blood container be placed so that the blood may just enter the Okay, you have to use the formula P is equal to H rho G. Find the value of H. Then next question 25. Derive Bernoulli's equation. We equated the work done on the fluids in the tube to its change in potential and kinetic energy. Then what is the largest average velocity of the blood flow in an artery of diameter 2 into 10 power minus 3 meter if the flow must remain laminar? Okay, you have to use the idea of Reynolds number. So Reynolds number R is equal to rho Vd by eta, and we will give you the maximum value. Okay, V is equal to data is given. For maximum value, you can take 2000 for Reynolds number and find the value of V. Okay, then next question, and there is a second part, I think. What is that? Do the dissipative forces become more important as the fluid velocity increases? Yes. See, when the fluid velocity increases, the possibility of streamlines to change into turbulence is high. Turbulence dissipates energy. So when velocity increases, turbulence dissipates energy, therefore the possibility of loss of energy increases. Then question 26, again same, you have to use R is equal to rho Vd by eta. R is equal to rho Vd by eta, so that velocity V you can calculate, substitute the values and find velocity V. And what is the corresponding flow rate? Again, flow rate is equal to rate of flow is equal to AV. So you can substitute the values and find the value of flow rate also. Then question 27. A plane is in level flight at constant speed and each of its two wings has an area of 25 meters square. Each wing is having an area 25 meters square. Therefore, the total area, there are two wings, 50 meters square. If the speed of the air is 180 km per hour over the lower wing and 234 km per hour over the upper wing surface, determine the plane's mass. Okay, so again here also we have to apply Bernoulli's theorem. We have P1 plus rho V1 square. The height difference you can neglect, by 2 is equal to P2 plus rho V2 square by 2. Okay, so from this equation you can find the value of P1 minus P2. Find P1 minus P2. Pressure difference you can calculate. Once you get the value of pressure difference, then you can see the force applied by the air, the upward lift you can calculate. Force is equal to pressure into P1 minus P2 is the pressure difference. Pressure into area. Area is 50 meters square. And this upward lift should support the weight of the plane mg. Then only the plane can move upward. So the upward lift is equal to weight of the plane, and from this the mass of the plane m can be calculated. Then next question 28, Millikan's oil drop experiment. What is the terminal speed of an uncharged drop of radius 2 into 10 power minus 5 meter and density 1.2 into 10 power 3 kilogram per meter cube? The data is given. You are asked to calculate the terminal speed. Terminal speed formula Vt is equal to in Millikan's oil drop experiment. You can see the oil drop is falling through a viscous medium. Then In such a situation, if something is falling through a viscous medium, then we have a formula 2 by 9 a square rho minus sigma into g by it. So you can substitute the values and you can find the value of terminal speed. How much is the viscous force on the drop at this speed? Okay, whenever an object is falling through a viscous medium, you need to apply Stokes' law to find the viscous force. 6 pi eta AB you have to calculate. Then question 29, mercury has an angle of contact equal to 140 degree with a soda lime glass. A narrow tube of radius 1 millimeter made of this glass is dipped in a trough containing mercury. Okay, by what amount does the mercury dip down in the tube relative to liquid surface outside? Okay, so this is a case of a capillary fall, and formula is H is equal to 2s cos theta. This is a surface tension. 2s cos theta over a rho g. Rho is the density of the mercury. Okay, you can substitute the values and you can find the answer. And it's given the angle of contact theta is 140. So cos 140, you can use the trigonometric equations which you have studied. Cos 140 is equal to minus sine 50. Your answer will be negative because it is the case of capillary fall. Find the value of sine 50 and substitute in the formula. You can substitute the remaining values to calculate the value of h. Then next, U2. Okay, U2 has two arms, and those two arms are having different radii, and both the arms are just like a capillary tubes. So you will get a capillary rise in both the arms. And what is the height difference? That is what you have to calculate. So we can take like this in the first one, the first arm, you have H1 is equal to 2s cos theta, same liquid, same type of tube, divided by A1 rho g. And in the second tube, you have H2 is equal to 2s cos theta divided by A2 rho g. You are asked to calculate the height difference. So H1 minus H2 is equal to 2s cos theta divided by rho g into 1 by A1 minus 1 by A2. You have to substitute all the values in SI unit, and you can find the value of the height difference in the two tubes. Okay, so that's all the numerical problems in this chapter. Thank you.